into the where we left off last time? Okay, so remember we talked about, so we're talking about these partial derivatives. We said with a multivariable function, we have there's two independent variables, and so we have a rate of change or a derivative for each of those, right? And so we want to know how z is changing with respect to x and how z is changing with respect to y. Okay, and so we're going to look at these partial derivatives in the four different modes of multivariable functions or representations. So we did a lot of the function definition last time. That was working on the formula, taking derivatives, right? So we left off with this example. Let's do this one again real quick. It's a fast one, and we're going to use it today. So first of all, the partial of this function h with respect to x will be, with respect to x, so 3x squared minus, what, 4y squared? And then with respect to x, this is just like adding a constant. It's like adding 5, because there's no x's in it. So the rate of change is 0. Okay, and then it says find that value at 1, 0.5. Or 1/1/2. So we're going to have 3 times 1 squared minus 4 times 1/2 squared. And I think we get a 3 minus 1 is that 2? Okay, and then similarly over here, h of y is going to be partial derivative with respect to y. That's just going to be 0. That's just like a constant added on. And then here, the minus 4x is a constant, but it's multiplied by our function. So that will make the rate of change that much greater. So negative 8xy, and then plus 4y cubed. Now these partial derivatives are themselves multivariable functions. What does that mean? That means that as you move around, as you choose different ordered pairs of x and y, you get a different rate of change every time. So there's a rate of change associated with every single pair of x and y. So they themselves are multivariable functions. So at 1/1/2, the rate of change is going to be negative 8 times 1 times 1/2 plus 4 times 1/2 cubed. So negative 4 plus 1/2, this is 1/8, negative 3.5. So that was finding the partial derivatives and then evaluating the partial derivative for a particular xy ordered pair, and we get this number. And we worked hard last time at the meaning of that number. It's a loaded, very loaded number, loaded with lots of different details to make sense of it. So we're going to practice that right now. So if this is the partial derivative with respect to x, what does that mean for y? How do we consider y when we're going to do this analysis on x?
When y is that value.
We're going to say hold y constant at what?
0.5.
At 0.5. We don't want changes in y muddying the waters here. We just want to focus and make this as easy as we can. Focus on x, right? So we're going to hold y constant at 1/2. And then what are we going to do? Then we're going to let x change. Let x vary by dx. So x is going to be what? It's going to start at 1, and then it's going to end up a little bit greater than 1. So the rate of change then helps us understand how z is going to change, our dependent variable, right? So the value of the function, or z. So now given the fact that the rate of change is 2, how will our z value change? Did anyone remember this from Wednesday? So what we're getting at here is, what is the meaning of this 2? What does that number tell us about this function, right? It tells us that when we're at 1/1/2, we hold y constant at 1/2, and we let x change a little bit. What's going to happen?
Is z going to change by that amount?
Is it going to change by 2? So z will change by 2. Is that right? How much will
Or it's 2 times dx?
That's right. Right? A rate of change is a constant of proportionality. It's how much z changes with respect to x. So if we let x change a little bit, this rate of change of 2 tells us that z is going to change twice as much as whatever our little change in x is. And it has to be a little change. If the change is too big, we'll get too far away from x equals 1, and the rate will be different. So this is assuming a constant rate in the local area, just the local area around 1/1/2. Okay, does that make sense? So this little equation is what frames our meaning for that 2. Given changes in x, the resulting change in the function, or z, is 2 times the change in x that we pick. Okay, likewise? Now we're going to analyze what's going on with z with respect to y. So what does that mean for x? What will we do with x here?
Oh, x constant at 1.
At what value?
1.
We're going to hold x at 1, right? We're going to hold x to be 1, and then we're going to let y change from, starting from 1/2 to 1/2 plus dy. So we have a change. We're going to change y a little bit. We're going to increase y a little bit. This rate of change then tells us the influence of changing y on z, or on the output of the function. So what will it be? What will happen to z when we change y by dy?
-3.5 from dy.
Yes, so however much we change y by, the resulting change in z, or the resulting change in the output of the function, will be -3.5 times as much as our change in y. And that's a review from last time, but we got to keep practicing it, because it takes you like a minute and several sentences to make sense of these numbers. These rate of changes have a lot of details packed into them, okay? And we want to understand that. Questions on interpreting partial derivatives or rates of change of multivariable functions? Okay, so let's transition now to the surface in R3. We want to look at the same situation. I've got H graphed in my software. We're going to look at this point 1/1/2, and we'll see how these partial derivatives show up visually with a surface in R3. So can I erase this? Any last chance for questions?
What does it say right in front of x varied by dx? What does that say right in front of it?
Let?
It says x.
That's let, L-E-T.
Sorry, what?
Let.
It's a let, L-E-T.
Okay.
Any other questions?
So we hold one variable, and that variable will be constant, right?
Yeah, that's always true for a partial derivative. If you're doing partial derivative with respect to x, we don't want y to change. We hold y constant. And if you're doing the partial derivative with respect to y, you hold x constant. You don't want that to change. Okay, so here's that same situation. Here's the function. I'm calling it f now. Okay, and we said it was h before. So we said that, what did we find? Let's change it to h. It doesn't matter. So we found that the partial with respect to at what, 1 comma 1/2, is that right? Was 2. And so what does that mean? It means for a change in x, so if the rate of change is positive, then what does that mean for z? How z changes at the point 1 1/2.
Z changes by 2 dx.
Yeah. And so will z increase or decrease? Increase, right? And so let's see that happening. So when we're looking at the partial with respect to x, we're going to hold y constant at 1/2. And here's that. So that blue plane is y equals 1/2. And so if we're talking about z with respect to x, we just stay on that plane. We look at the surface only on that plane where y equals 1/2. And what do you notice? As x increases, what does z do?
Z also increases.
Yeah, do you see that z, if you just follow this like kind of parabola shape like this, that's the surface, that's staying on the surface, keeping y constant at 1/2. And so we see that if you let x increase, that's an exaggerated increase by dx, then the rate of change is positive, so z goes up. And how much does it go up?
dx.
Yeah, 2 times dx. At that moment, right? At that point, 1 1/2. If you increase x a little bit, you can see that the surface or the z value is going up by twice as much.
So is that that section of the curve similar to a parabola?
Well, maybe. Let's see. If you plugged, yeah, maybe. So if you plugged y equals 1/2 in here, it looks like a cubic. That's actually going to end up being a cubic function because you'll have the x cubed. So it's not a literal parabola like an x squared function. It's actually this is actually a cubic curve.
Okay, because what I was thinking was since the derivative of a parabola is 2x.
No, just coincidental. It's just what we happen to get at this point. Because as soon as you move to a different point, you're going to get a different rate of change, right? This rate of change only pertains in a small local area around 1 1/2. So you only can look at you can only use this rate of change in a small local area around 1 1/2. Because these partial derivatives themselves are a function. As soon as you move to a different location, you get new values for the derivatives, new rates of change. And you can see that because this surface is wavy, it's curvy, like over here, my rates of change will be totally different than they were here. So that's just, the 2 doesn't mean that it was quadratic. Okay, so now let's look at partial with respect to y. And when we did that, we calculated it as negative 3.5, and that meant holding what? X as 1. So let's show that. So before we get in detail about the number, what does it mean that the rate of change is negative? So just in general, what does it mean that rate of change is negative? Yeah, we expect that when y increases, we expect z to go down, right? And now the value tells us how much it goes down, right? It's going to go down 3.5 times as much as any change in y that we can make. Okay, so here is x equals 1, this purple plane. So we want to staying on the surface for x equals 1 means staying on the purple plane, or kind of following this trace right here. So that's staying at x equals 1. Try that again. Try it one more time. Further this way. There we go. Okay, so we want to stay right there on that's staying on the surface and holding x to be 1. And so what do we see? If we let y increase a little bit, that's going kind of like this. That's like a dy. So first of all, is our conclusion right? Does z go down? Yeah, as you increase y, z is going down. Negative rate of change, right? Negative rate of change means decrease of our quantity. And then how much does it go down?
Negative 3.5 times dy.
That's right. So now I'm going to... Okay, so that's dy, that little increase in y right there. And then as a result, z goes down. We end up there. Negative 3.5 times dy is the change in z that we get. So a decrease of 3.5 times as much as the increase in y that we pick. Again, this has to be a small change, because as soon as you move away from the point 1/1/2, the rate's different. So you can't do this anymore. This is based on what proportionality of changes that only holds in the local area. So that's like assuming a constant rate, right? Constant rate of change. Which is only a safe assumption for very small changes in y. Okay, does this make sense? So let's look at another example of analyzing the surface. Can I erase and move on from this one? Any questions?
So it's starting at 1/2 y?
Yeah, we start at y equals 1/2, and we let y increase a little bit from 1/2.
Okay.
And then we see what z does. Z goes down, and it goes down 3.5 times as much as whatever dy we pick.
And this is an estimate based on the slope at that point.
Yep, it's an estimate, right? So, but if dy is small enough, it's like essentially the same, right? If dy is a small enough change, then you have local linearity, right? Right there at that point, you can assume it's essentially linear, and this holds for very small changes in y.
Yeah, because it's so close.
Right, but as soon as y starts getting bigger, then it's you're staying on the tangent line, and the surface is curving, and now you've got error, right?
Yeah.
Okay, let's look at another example. Let's go back to the guitar string. I've got the graph of that one. Pretty cool. So here's the guitar string function. Remember, that was this function here. And let's just review what the coordinates meant. X was the distance from the end of the string in millimeters. Let's do it on an axis. So X, and that was the distance from one end of the string in millimeters. And then the y-axis was time in milliseconds. Time since we plucked. Time since we plucked the string in milliseconds, and that's the y-axis. Okay, and we looked at 70 and 2.5 milliseconds. Yeah, 70 millimeters down the string, 2.5 milliseconds, and I think we got the partial with respect to x was negative 0.33, and the partial with respect to y we got was 5 point something, 5.4? I think it was 5.43. So what does that mean for the surface at 72.5? What do we expect this does? What does this tell us about the surface?
It decreases.
It goes down if you increase what?
Increase x by 70.
Not by 70, by just a little bit. Okay, so we're at 70. We're at x equals 70, and we increase x by a little bit. We expect z to go down. Go down a lot or a little bit?
Small amount.
A small amount. It's going to be this much times whatever dx we pick. So let me show you that.
And I'm trying to remember, z was distance. Wait, yeah, that was just distance from a straight line, right?
What's that?
I'm trying to remember.
Oh, displacement. Yeah, the z, yes, that's good. We should review that. The outputs of this function, the z values, were the displacement of that point on the string from at rest.
Is that perpendicular?
Yeah.
Okay.
Okay, so here is this green plane then represents holding time constant at 2.5. And what happens when you increase z a little bit, or sorry, when you increase x a little bit, what do you see?
Going down.
Going down. Negative rate of change, right? Negative rate of change, surface heads down. How much does it head down?
0.03.
So that's our dx. Resulting change in z is it negative 0.33? Times as much as dx. It's proportional, right? Proportional. Okay, so y, so this is freezing time at 2.5 milliseconds, and y is changing time, and then x is the distance down the string. So this is x equals 0 is at one end of the string, and then the other end of the string is at this like maximum x value here. So this is kind of like the length of the string here, and then time going by. So well, let's just let's just do put that on hold for a second. Let's go back to this. So what will it mean that the partial with respect to y is positive 5.43? What will that tell us about the surface?
Z changes by 5.43 times dy.
Yep, and will z go up or down?
Significant increase.
Up, right? So you see that would be holding x constant at 70. And then you'd have this trace on the surface like that. And what's happening to z? As you go in the y direction, z goes up. Positive rate of change, right? Positive rate of change means z goes up when you hold x constant. But when you hold y constant, z goes down, according to that green trace there. That's why, and we have a negative rate of change. Okay, now back to what I was talking about. Let's erase this.
So the y curve is I don't get it.
Holding, so that relates to the partial with respect to y. That's holding x constant. So holding x at 70, right?
Yeah.
So if I put a plane at 70 here, it would create a trace like this.
Oh, okay.
That's holding x constant at 70. And you see that if you increase y a little bit, z goes up. It's going up. Positive rate of change means that z increases when y increases.
Thank you.
I mean, it makes sense because it's going to keep oscillating.
So here, check this out. It's pretty cool. So if I let that green plane increase, it's like time going by. So it's like letting time increase. And then we said the x coordinate was like the string here, this end of the string to this end of the string. So that trace that's formed, what is that trace that's being formed between the plane and the surface? Anyone see what you're looking at there? You watch the intersection of the two? What is that?
And the rate of change.
Oh, that's almost like a change in the shape of.
Yeah.
So again, this way is distance down the string, and every green plane is a moment in time. So does anyone see what you're looking at there?
Oh, yeah.
So if you made that into a whole bunch of lines parallel to the y-axis, then you would have each point on the string and its position, basically.
So what is that blue intersection?
String vibrating down.
That's the guitar string.
Yeah.
That's the guitar string vibrating up and down as time goes by. Now it's greatly exaggerated and greatly slowed down. Okay? But that's your guitar string because your x coordinate is distance down the string, string, and then the green plane is different moments in time. So time is increasing, and this is the guitar string actually vibrating. And that's shown by this sweep of traces on that surface.
I mean, technically speaking, the bending of the string is going to be from one point, from where it's connected at the top to where it's connected at the bottom, because there's nothing really holding it in the middle.
Right. That's what makes the sound, is the string vibrates, and so it's displaced up and down like that. Okay, cool. So let's move on here. So we've talked about these partial derivatives in terms of the function formula using your derivative rules. We talked about it in terms of a multivariable surface, especially looking at if the rate of change is positive or negative, that z would increase or decrease in that particular direction. So we did that, a couple examples of that. So next thing we want to look at is a table of values. So how do these partial derivatives, how do we conceive these partial derivatives with a table of values? So here's a cool table of values multivariable function. And this is a heat index function. Heat index function. So heat index is, we'll use capital I, heat index, as a function of temperature outside, actual temperature outside, and relative humidity. So we'll say temperature is T, humidity is H. And so this function gives values of heat index, which is like perceived temperature. And that's also in degrees Fahrenheit. So this temperature, this independent variable temperature, is actual temperature in degrees Fahrenheit. The output of your function is also degrees Fahrenheit, but it's like how hot it feels, or the perceived temperature. Okay, and that's a multivariable function. Given a, for instance, given a temperature 90 degrees and a relative humidity of 45, the function tells us what the perceived temperature is. And what is the perceived temperature when T is 90 and H is 45?
93.
93. So the values in the table are values of the dependent variable. They're like z values, right? For a given x along this kind of axis, and also a given y. So so we got I of 90 comma 45. So I of 90 comma 45 is?
Our z is measured as heat index.
Heat index, perceived temperature.
Perceived temperature, okay.
What it feels like.
All right, thank you.
Yeah. So that will also have units of degrees Fahrenheit. Okay, so that's just utilizing the function. So at 90 degrees outside, 45% humidity. This is a pretty realistic monsoon situation for here in Arizona. It feels like 93 outside. Okay, so now what about partial derivatives? What about rate of change? Okay, so we said that changes in index could be found two ways. How could we find a change in index for a given change in temperature? What would we need if we had a given change in temperature? What would we need to find the change in index?
So the holding the heat derivative is constant.
Right. We need the partial derivative of heat index with respect to
Is
temperature.
sorry.
Oops. Okay, so given a little change in temperature, we know that if we multiplied it by that partial derivative, we would get the resulting change in the heat index. Okay, so that means, what does the partial derivative equal? We could write it this way, IT. And we're going to look specifically at 90 and 45. But based on this formula, how can we estimate the partial of heat index with respect to temperature? What could we do?
Couldn't you pick two values of temperature and then subtract one from the other?
Okay, but what? How are we going to calculate it then? Yeah, that's part of it. So what will the calculation be to get this partial derivative?
The change in where you pick two values for temperature.
Yeah, it'll be di divided by dt, right?
Yeah.
So we're going to get a change in temperature. I think this, some of you were saying this. You're going to get a change in temperature, corresponding change in heat index, and set up the ratio. And that will be an estimate for the partial derivative. Okay, so at 90/45, what are we doing with humidity? For if we want the partial of index with respect to temperature, what are we going to do with humidity?
Stays constant.
Stays constant. So we're going to like kind of hold it constant here at 45. Okay, so we're going to be focused on at 45 this. And so the table kind of dictates the change in temperature that we have. What change in temperature do we have to use here?
2.
2, right? The table is based on changes in temperature of 2.
Oh, that's why it's lowercase delta.
Okay, so changes are 2 in temperature. And then what change in index do we get for changes in 2? Well, how much change do we get there? Plus 4. How much change do we get on the other side?
3.
Plus 3. Well, there's nothing better about on this side than this side, so we'll just call it the average. Okay, so an increase of 4 on this side, an increase of 3 on this side. The best we can do is just kind of average those together. So for around 90, for every change in 2 degrees, we're seeing about 3.5 change in degrees perceived. And so that is 1.75. And that's going to be degrees Fahrenheit perceived per degrees Fahrenheit actual. Don't make those go away. One reason is they're different. They're the same unit, but they're different. And the other reason is you never want to cancel these units out because rate of change requires 1 unit per another. So whenever you have a rate of change, never cancel the units. Never cancel the units.
And just a reminder, that's only for that specific spot, because if you start moving further down at the 45 humidity,
Yeah.
then it starts getting up to 5 and 6 change.
Yeah. Well said. If your change is too big and we end up here at 96 or 98, well, now your changes in index are different. It's a different rate of change over here. So this estimated rate of change is only in the local vicinity of 90 degrees Fahrenheit, 45 degrees humidity. Okay.
I'm just wondering, wouldn't a good way of differentiating between the 2 degrees Fahrenheit, the ones stacked on top of each other, either use subscript, like maybe an A and maybe a I, one for actual and then index.
Well, we know that. We know that I means index and T means actual temperature. So
No, I'm talking about the 1.75, like.
Sure, if you want to add something on there, that's okay. But we know because we know this one is for this, and this one is for this. Okay, let's do it for humidity now. So for humidity, question.
So I understand that the rate that we get is only relevant to that little section.
Right.
But what I'm confused about is how this is useful in general.
Because we'll see in a second. I'm going to actually give an example in a second.
Okay.
But the one thing it's useful for is understanding rate of change, and that rate of change is a varying quantity throughout this function. Right. So I mean, to say that the rate of change doesn't matter here is to say that it doesn't matter anywhere. Does that make sense?
Mm-hmm.
So, I mean that's kind of the whole subject matter here is what is the rate of change of a function? Well, that itself is a function that changes, and so let's go on. I think we'll see an example later in class. So how about the partial with respect to humidity now at the same place? What will we do now in terms of temperature?
Assume it's constant.
Hold temperature constant.
We're going to hold temperature constant at 90 and just look at what changes in humidity, resulting changes in index, and what's this constant of proportionality, the rate of change. So what changes in humidity are we? So this is going to be dI per dH now, approximately. And then what? So what changes in humidity are we kind of locked into here? 5, right? So we see in the table, we only can, estimate based on changes of 5. And how much change do we see here?
2.
Plus 2. Plus 2 again. So how is the index has changed? It's increasing by 2 degrees Fahrenheit for every 5%. So I think that's 0.4 percent Fahrenheit, or degrees Fahrenheit per percent. Okay, so we're going to do another example of calculating these rates. We're going to move somewhere else in the table and get new rates. Any questions on what we're doing here?
Are we doing 2 and 5 because it is a chart and there'd be a lack of data if we tried to change the ratio there?
Yeah, and if we tried to like anything we could introduce in here, like in between, would just be based on the 2 over 5, right? So the best we could do introducing new data would be based on what we have. So there's no point in trying to get, there's no point in trying to make a smaller change in humidity because we don't have any more information than this. Okay, so let's move to, I'm going to move to temperature of 82, humidity of 90. So temperature, and so as I'm erasing and getting started, you can try it. Find the partial derivative of index with respect to temperature, and find the partial derivative of index with respect to humidity, and see if you can get out ahead of me. Maybe turn your speakers off, and see if you can get out ahead of me, and see if you can get it before I do, okay? Okay, so what are changes in H? What changes in H are we looking at here? Sorry. Did I do T first before?
Yeah.
I'll do that. I'll just stay with that. So if we're changing temperature, what does that mean about humidity?
Humidity stays constant.
Keeps humidity constant. And then what changes in temperature are we kind of locked into here?
4, 6.
What change in temperature? Change in temperature is 2. And then, so there's a change of 5 and a change of 7. So a change of 5 in index on the left side, a change of 7 on the right. So 6. So 3 degrees Fahrenheit per degrees Fahrenheit. Did some of you get that?
Yeah.
Okay, and then do the index with respect to humidity at 8290, which is approximately equal to dI per dH, which is, so now we're looking at fixing temperature, and our dH is, again, it's still 5. And then we have an increase of 1 in index, increase of 2 in index, so 1.5. And I think that's, what is that, 0.3? And that's degrees Fahrenheit perceived per percent. Okay, so here we are at 82. Any questions on that? So we got this rate. Those are our 2 partial derivatives. Those are our 2 rates of change. Okay, so it's 82 degrees out, 90 degrees Fahrenheit. and the temperature goes down half a degree. The temperature is going to, here we are, it feels like 91 out. The actual temperature is going to go down 1/2 of a degree. What can you conclude? So this is kind of a test of all the stuff we've been practicing for the last 2 days in class. Temperature is going to go down 1/2 a degree, and what could you say about that? Or what could you observe or conclude?
We could decrease by 1.5 degrees Fahrenheit.
Yeah, that.
Okay, right. So what I'm saying symbolically is I'm saying dt is negative 0.5, and we know if we have the partial derivative with respect to t, that tells us what? It tells us that
di is equal to our constant times dt.
right. So for a change in temperature, a small change in temperature close to from 82, the resulting change in index will be 3 times that change in temperature. Remember saying that over and over again? So what does that mean? It means if the temperature goes down 1/2 a degree, then what it feels like will go down 1.5 degrees. All right. What would you say if the humidity went up by 2%? So say we're here 82, 90 degrees, and the humidity goes up by 2%.
It would feel like the temperature went up by 0.6.
Okay, so now they're changing, and we have the rate of change, and we have a change, so that we can figure out how much the perceived temperature is going to change. It's going to change by 0.3 times. Right, so what does this rate of change mean? It means given any change in humidity, I just gave you one, the perceived change in temperature will be the rate of change, 0.3 times that change in humidity. Or how much?
0.6 degrees Fahrenheit.
Okay. Now, what if both changes happen? What if it goes down 1/2 a degree and the humidity rises by 2%? Both happen. Now what can you conclude?
Would it feel like the temperature decreased by negative 0.9 degrees Fahrenheit?
So you want to add these. So he's saying if you change temperature by this much and also change humidity by this much, to get the overall change, we'll just simply add the 2 changes that we got. What do the rest of you think? Agree?
Yes.
I have 2 people agree. Yeah, because the whole point of looking at these partial derivatives is they're totally separate, right? X and y are orthogonal to one another. Changing x means holding y constant. Changing y means holding x constant. And so this change, due to the change in temperature, had no influence on changing on humidity. And humidity has no influence on this. Likewise, changes in temperature have no influence on this. Therefore, if both changes occur, then di equals
The combination of the 2.
the sum. It's going to be the change in index we got from changing the temperature plus the change in index we got from changing the humidity. Just sum them up. So it'll be negative 0.9. So if both these changes occur, it's going to feel like the temperature went down almost 1 degree. So if both those changes occur, then what's the new perceived temperature?
90.1 degrees.
You think it's what now?
90.1.
Right, and how are you getting that?
Just subtract the change in your perceived temperature from the original perceived
Right.
temperature.
We were at 82 degrees Fahrenheit and 90 degrees humidity. By the way, don't worry about the quiz. I'll tell you about that later. Just focus here. So we're at 82 degrees and 90 degrees humidity, and that it feels like 91 degrees outside. We saw a change in temperature, a change in humidity. Those two together made the temperature feel like it changed this much. So now the new perceived temperature is going to be, man, oh man, these things. You can't see it, but I can. Get my way. All right, so then the new perceived temperature is?
I plus Ti.
Maybe the old perceived temperature plus the change in perceived temperature, which is 91 plus negative 0.9 equals 90.1 degrees Fahrenheit. Can you still read the bottom of my screen here?
Yeah.
Good. So yeah, so new perceived temperature equals the original, the 91, plus the changes in perceived temperature due to changes in temperature and humidity, which was the combination of the negative 0.9, the negative 1.5, and the 0.6. Okay. Do all the numbers make sense and where we got everything? Does that, anybody have a question?
All right, now we need to add in the factor of stepping into shade.
Doing what now?
In Arizona, if you step
Oh.
underneath the shade,
Yeah, right.
that's amazing.
There you go. Okay, so where we're going next? So we've isolated the two partial derivatives, and we talked about isolating changes. And so now what we've done is we said, okay, let's let changes in both the independent variables happen simultaneously. Okay, when we do that, we get a combined effect of a change to our dependent variable, which was our heat index. Okay, what also happens when you take combined changes of your two variables like this, there's a rate of change associated with combined changes. All right, and that rate of change is going to come from a combined effect of the two rates of change, the two separate rates of change. So that's where we're going next. So far we've talked about just the two separate rates of change, the partial with respect to x, the partial with respect to y. But we can consider changes in both, not holding either one constant, but letting both of them change. And then what would the rate of change be then? What would the rate of change of heat index be for a certain combination of changes of both variables? So we're kind of knocking on the door when we did this problem here. We got this change from 91 to 90.1. Well, that was a rate of change. There was a rate of change that took us from 91 to 90.1, and that rate of change was based on both of them, both of the separate rates of change. So that's what we'll start on Monday. Okay, any questions? All right, so what we'll do with the quiz is, so I need to still compile the quiz, and I'll as soon as I compile it and it's ready and open, then I'll send an announcement out, and it'll just remain open indefinitely. So you still have the 7 minutes from when you start, but there's not really a closing time. But you want to take it as soon as you can while this is all still fresh. So take it as soon as I send the announcement. Take it as soon as you can after that. Otherwise, again, you have the written homework due at 5. I can stick around and help with that after class. You've got 2 webworks due early next week. And then your quiz, once I get the quiz open for today's stuff. Any questions before we sign off? All right, then have a great weekend. And again, I'll stick around for questions.
Have a good one.
You too.
Thank you.
You're welcome.
I had a question about the homework.
Sure thing. Well, actually, is there any, let's definitely get to that. Any questions on what's I have on the screen here, this last example in class, before we...
Professor, it's just that I'm still kind of in the, because the one here perceiving the new temperature for the DI is, I still not wrap my head around that one. And why we have to take the one that we found, the negative 0.9, to add it to the one up here
So the difference is this is the change in perceived temperature, how much it varied due to these variations in temperature and humidity. Okay? So that's DI. Then I asked, okay, what do you predict the new value of I to be, the new heat index to be? Right? So what is the new perceived temperature? This was how much we perceived that it changed, varied. So what is the new perceived temperature? So it used to be 91. And then it changed by this much. So now what do we perceive the temperature to be?
91.
Do you see that? So it's the original, what it started at plus how much it varied will give me the new value.
So looking at the new temperature, the perceived temperature, how can we tell this one on the table given?
On the table?
Yeah.
So in the table we were here, and what did I say? DT was -0.5. So we went a little bit this way, right? A little bit this way. And DH was 2, and we went like this way. So we kind of from this 91, we kind of headed like this direction here. See this?
Okay.
Right? Decrease in temperature by half, so going to the left, and then increase in humidity of 2, which is going down on the table.
Oh, that makes sense.
So our new temperature was like what, 81.5, and our new humidity was what, 92. So we're estimating, this is estimating, nice 90.1 is estimating what you would get in the table right there if you had the 92 and the 81.5.
Oh, okay.
Does that make sense?
Definitely.
What's that?
Thank you.
Yeah.
Definitely. Thank you so much.
You're welcome.